Our first paper today is Approximate Dynamic Programming Captures Fleet Operations for Schneider National, presented by Hugo Sameo from Princeton University. Hugo?
Good morning. The work that I'm going to be presenting to you today is the result of a collaborative work between Castle Lab at Princeton University and Schneider National. Roughly, the outline of my presentation will follow the steps on the screen. I'm going to try and give you an idea of what is the problem that we are tackling. Then I'm going to try and describe the basic methodology that we use to optimize. Then I'm going to tackle some of the algorithmic challenges that we faced in that realm. I'm going to then talk a little bit about the efforts for calibration and validation of the system. And finally, Ted Gifford from Schneider is going to tell you some of the policy studies that have been performed with this system. So, moving now to the operational problem. Schneider National is one of the 3 largest truckload companies in the US. So they manage approximately 15,000 drivers moving loads across North America. And the specific portion of the network that we were interested in helping them with modeling was the so-called one-way network, which comprises about 6,500 drivers of different types, moving approximately 50,000 loads in every 4-week period. And when Schneider is solving this problem, Schneider is trying to balance several factors at the same time. So balancing the empties that the drivers have to move, meeting the customer service requirements in terms of pickup and delivery, trying to get drivers home as often as possible, and also meeting complying with the DOT regulations with respect to the hours of service of the drivers. So our challenge was to try and provide Schneider with a system that could simulate the operation of the company, which is controlled by these operators in their dispatch room in Green Bay, Wisconsin, so that then Schneider would be able, with this system, to do policy studies, like, for instance, these ones that I'm listing here, and which Ted is going to be talking to you later on in the talk. So now, modeling and optimization. In the 80s, a problem like this would have been modeled for each type of driver individually through a network flow problem in which you have the time and space dimensions, and you would use some linear programming software to solve this. As computers got bigger and also the linear program software improved, we were able actually to solve simultaneously these networks for several types of drivers, thus modeling the interaction between the networks. But still, questions remained, for instance, with respect to how would we incorporate uncertainty, stochasticity, into this modeling. Uncertainty, for instance, in transit times, uncertainty, for instance, in the time in which loads are booked, so the delay from when we know about the load and when it can move. So our proposition to solve this problem then is to use dynamic programming. Dynamic programming, in the first approach, we need to define what is the state of the variables. In this case, we have 2 basic resources. We are trying to assign drivers to loads. So we are going to use multidimensional attribute vectors to describe these 2 resources. For instance, for the drivers, we are going to have an attribute vector with 15 dimensions. Some of those items there actually turn into several items. We are going to call that, for instance, A, lowercase a, attribute vector, and we are going to refer then to the number of drivers of a given type A available at time t by R sub t A. Similarly, we are going to refer to the loads by an attribute vector also, say B, and the number of loads of type B available at time t, we are going to describe by D sub t dB. So now we can then describe the state of the system by the pair of multidimensional vectors describing all the drivers and all the loads that we have available for all types at a given point in time. It is a rather large vector set of vectors, and therefore the state space is very large. We want to solve an optimization not only at each point in time, but principally we want to solve this optimization, this assignment of drivers to loads over time. Our proposition is to use dynamic programming. But as most of us probably know, dynamic programming has difficulty with very large problems like the one that we are proposing to solve. One of the sources of problems is the so-called curses of dimensionality. It's the state space that is huge, that's virtually infinite, as we already mentioned too. Also, that expected value that appears in the objective function there, the outcome space related to that expected value is also very huge. And finally, the state space of the decision variables is also very large. Related, we have computational challenges with dynamic programming. And these computational challenges go from how do we compute actually these value functions, how do we compute that expectation, and last but not least, how do we solve this optimization problem. So we are going to propose to use an approximate dynamic programming strategy, which is based on these 3 points that I have on the screen. We are going to use the concept of post-decision state variable to simplify the objective function. We are going to then propose certain approximations for the value functions. And finally, we are going to propose also certain strategies to obtain the value of being in a certain state. Let me give you then a brief idea of what is a post-decision state variable. So suppose that at any given time, we begin with the description of the system given by the 2 vectors that we mentioned before, RT and DT. Okay? And suppose that now we choose a set of decisions, optimal assignments of drivers to loads at that point in time. So the state of the system, before I did that decision, I call it pre-decision state. The state of the system immediately after I made the decision, but before I roll the clock, so before anything else happens, I will call that the post-decision state. So please notice that no uncertain event has still happened. Now I bring into my system any extraneous, exogenous events, like, for instance, arrivals of new drivers to the system, new loads that are called in, or we become aware that a certain driver is delayed in transit. So with those pieces of information, now we are able to obtain the state of the system at the next point in time, which then becomes the pre-decision for the next point in time. The effect of using that post-decision state system description is that now our objective function, we can remove the expectation because the post-decision state involves no uncertainty. So we now have an optimization, a deterministic optimization problem that we can solve to find out what are the assignments that we want to make of drivers to loads. And then we solve separately the problem of approximating the expectation of the value function using then statistical and or machine learning techniques that we have employed for that purpose. But further, I mentioned also that we still need to approximate the value function. We have been able to remove the expected value, but we need to approximate the value function. For this particular problem, we have concluded that linear approximations on the number of drivers of each type at each given point in time are sufficiently good to model the value functions. And so that's what we do. So finally, in this slide here, I can give you an overall view of the approach, the approximate dynamic programming algorithm that we use. And I am highlighting in color here, green, blue, and red, the main steps of this algorithm, which comprise, at any given point in time, first, the solution of a deterministic optimization problem. Then, with some of those results, we do a statistical update of the value functions, which is in blue. And then now, through Monte Carlo sampling, we incorporate any uncertainty in the evolution of the state of the system, and we find out the state of the system in the next period of time, and then we repeat the step for the next period of time. Pictorially, if I wanted to give you an idea, at a given point in time, we solve a deterministic problem using approximations to the value functions. Then we update those value functions. We incorporate then the Monte Carlo simulation. With that, we find out the state of the system at subsequent points in time, and we solve again the optimization problem, and so forth. We repeat this whole process once, we repeat this process twice, and through this iterative process, we are able then to calibrate, to estimate the value functions. In the process of doing that, there was a number of algorithmic issues that arose, and we singled out 3 of them to talk to you about. So even though we have been able to simplify the objective function, get rid of the expected value, and approximate with a linear function, still the truth is the state space estimating these value functions within the state space of these drivers with 15 dimensions still remains impractical. On the other hand, we know that we want to optimize these problems using the full range of attributes in the attribute vector. But the estimation of the value functions, we made a conjecture that we do not need those value functions to be evaluated at the full-fledged 15-dimension attribute vector. So what we proposed, what we imagined was, suppose that instead we calibrate value functions with, say, for instance, only 4 of those 15 attribute vectors. Well, it's better than 15, but it's still a very large state space. So we went further in this proposition for aggregation. So what if we actually had a family of different levels of aggregation so that we could then calibrate all these 4, for instance, levels of aggregation of value functions and use them in the optimization? Well, in order to do that, we had graduate work done in Princeton over the years, which helped us with defining this weighted average that we propose to actually produce for us the estimate of the value function for a given driver that we are going to use effectively in our optimization. And the basic property of these weights, I won't go into much detail, but the basic property of them is that they are inversely proportional to the variance, the estimate of the variance in the estimation of the value functions, and inversely proportional to the biases that aggregation brings into these value functions. And the other thing that I wanted to point out is that these weights, not only they depend on the level of aggregation, which is G, but they also depend on the specific attribute vector. So for the same level of aggregation, depending on how much data we have for a particular set of attributes, we may have more or less observations, statistical observations. In this graphic here, I wanted just to illustrate one of the desirable properties of this set of weights, which would be for more aggregate levels, the weights would begin higher in the first iterations, and the average weight for each one of those levels decreases as the iterations go by. Whereas for the more aggregate levels, the weights begin smaller and they increase over the aggregation, over the iterations. Something else, another test that we did with these aggregation levels, instead of using, say, the 4, let's suppose that I used only the most aggregate level of value functions. We see that the evolution of the value function, of the objective function of the problem, it quickly reaches a certain level and then stays at that level. But that's not an optimal level. Because if we use, for instance, only the disaggregate one, slowly it grows to a level of objective function, which is better. The behavior of the hybrid approach when we do the combination of the several levels is what we would expect. We quickly rise to the good level of the objective function. The other issue, algorithmic issue that we faced, the estimation of the value functions is based on an exponential smoothing formula, like the one that we are showing now on the screen. We're given a current estimate of the value functions and a new marginal value. We want then to combine those into a new estimate. We use then these step sizes, also referred as learning rates or smoothing factors. The issue here is the choice of the step size. Even, for instance, if we chose a step size like, for instance, 1/n, which decreases with the number of updates that we do, which is theoretically proven to converge and to be nice, there are certain data sets, like the one, for instance, that we are showing here in blue, and the theoretical curve behind that is the red one, in which even with such a good theoretical step size, convergence is very slow. So again, graduate work done at Princeton over the years allowed us to use a set of step sizes optimally developed to minimize the error of the estimation of these functions. And these terms, again, they have embedded in them this optimal step size. They have an estimate of the variance of the data and an estimate of the bias in the approximation. And they have been designed in such a fashion that as the noise increases, we want these step sizes to decrease towards 1/n. And as the noise decreases, but the bias may be bigger, we want these step sizes to be bigger and approach 1. this graph here, I had a case of a function that I knew what the optimal is, and I used several different step sizes to try and approximate that function. One of which was the optimal one. It's this pink curve here. 1 over n was there, and some sort of hybrid between 1 over n and constant. And you can see showing here the percentage error that using the optimized step sizes, we get a convergence towards the true value faster than using the other ones, which was the property that we wanted for these step sizes. The final algorithmic challenge that I would like to mention to you here has to do with the fact that even using such high-dimensional vectors as we have been using to describe drivers and loads, there simply are certain behaviors, corporate behaviors of the company that we were not able to fully mimic, emulate with the system. Like, for instance, the fact that the companies, in general, it tries to assign team drivers to longer loads. But if necessary, they will also assign shorter loads to those drivers. So in essence, we wanted to try and match the average length of haul per type of driver in the network. And the way that we devised to do that was by adding pattern matching terms to the objective function. And the way that we did that was by adding a term to the objective function where we try to minimize the difference between the decision made and some observed historical pattern. This term has a scaling factor, has a quadratic function on the difference between the decisions made and the observed historical factors. This was also the result of graduate work done at Princeton by some other student, which we were able to incorporate into the system. And this picture here, I just try to give an idea of the effects of using this pattern matching combined with approximate dynamic programming. So here I am showing you a band. This gray band is upper and lower bound on the average length of haul for a specific type of driver. So we would like the performance of the system to be as well as possible within that band and as possible close to the center of it. So the red curve, I tested various compositions here with the value functions, with patterns, only one of them and both of them. And as you can see, using the combination of value functions with pattern matching provided us with the better matching. So now I would like to give you a brief idea of the work that we did for calibration and validation of the system. In terms of calibration, before Schneider could actually use this system for policy studies, they wanted to ascertain that a number of corporate measures of the performance of the network, that the system could actually match those numbers. And so we did calibration of the system, and after doing the calibration, indeed, for instance, here on the screen, I am showing you average length of haul, and I'm showing observed historical mean and max for 3 different types of drivers. After the calibration done in the model, we were able to actually stay within the band of the observed historical values for this particular measurement. Simultaneously, there are a few others. I'm showing you here a couple more of them. For instance, the average revenue per tractor. Again, same thing, values observed and what we obtain. And finally, average utilization. In terms of validation, besides calibrating the system against these measurements, these corporate measurements, we also were very interested in knowing whether our approximation of value functions, so those marginal values of drivers, how accurate those were. So here is the experiment that we devised. We chose one specific type of driver, let's say solo drivers based in Dallas. And for that driver, what we did is we added, say, 5 extra drivers of those in the network. And then we run simulations, several simulations, to find what was the added value of those drivers in the network. And then we plotted all the results here and calculated the average. We did that for 10, 15, 20, 25. So this blue curve that you see in there is the result of these several simulations for adding successive drivers. Now, pick up then our system after we calibrated the value functions. Let's pick up the value function that we estimated for that type of driver, which is a number, it's linear, and let's see if multiplying that by the number of driver, how good we match the experimental result. And you can see that there is a band which goes up to around adding up to 20 to 30 drivers to the network. We match very closely what we obtain with the simulation. Similar to that analysis, now instead of one type of driver, I picked up 20 different types of drivers. For one of those drivers, I added to the network, say, 20 drivers, and I repeated that simulation several times. With the results of that simulation, I built a 95% confidence interval for the amount of revenue added to the network. I did that for one type of driver, I did that for another type of driver, and repeated that for the 20 types of drivers. So, and then in pink, I plotted the value functions that I obtained, again, from my single run of the system. And you can see that in 20 of those cases, in 18 of those, we were within the 95% band, whereas only 2 we were not, which is very close to 19, which would be the expected number. So this is what I wanted to show in terms of calibration and validation, and I turn over now to Ted to talk to us about some of the policy studies. Ted Gifford, please.
Oh, sorry. For about 25 specific studies over the last 4 years, and they've varied from fairly small ones to some that are pretty significant, and they've ranged from having clear financial benefit to simply providing some insight, or in some cases, giving us some ammunition to improve a negotiating position with a customer, for example. What I'll do is take, we have, I've got 6 here listed, but I think I'll just take 3 of them and discuss them in a little bit more detail, and certainly in the question session, be happy to explore some of the others. The first one involves scheduling drivers' time at home. Now, in a long-haul freight network, our drivers are typically out on the road from anywhere from 1 to 3 weeks, and then they get back home. Now, getting drivers home is a trade-off between providing a quality of life dimension for a driver and not too adversely affecting the impact on the efficiency and productivity of the network. Because whenever a driver goes home, if there is not a convenient load that takes him near his home at the right time, or coming out of his time at home session, if there's not a convenient load that he picks up fairly close to home, we incur a significant amount of deadhead. The main issue here is that in order to hire and retain drivers, it's important to address from a financial perspective these quality of life issues. Driver turnover in this industry is historically high. I think the industry average is close to 100% turnover. Ours has been in the 60% range, but a single point of turnover translates into somewhere around $5 to $7 million a year in added costs associated with hiring and training, and less experienced drivers having higher accident rates and those kind of things. So what happened here about 3 years ago, when it was very difficult to hire drivers, the operational side of the organization decided to implement a new policy that would allow drivers a considerable amount of flexibility to schedule their own time at home. And the operational people, to estimate the cost of this, ran a pilot with a small percentage of the network, and then tried to extrapolate that to the broader organization. Their estimate of the network impact to efficiency was in the $5 to $7 million range. Well, that didn't smell right to us, and the simulator provided a perfect opportunity for us to simulate various policies associated with the flexibility of getting drivers home. We determined that the cost of scaling this pilot up to the organization would have been $30 million a year. And because of the things that Hugo mentioned about validation and calibration, we were able to establish a high level of confidence with business leaders that the simulator actually made sense and would give results that were of value. So in fact, in running the simulations, the simulator actually helped us find a alternative approach that involves stratifying drivers by different time at home profiles, and we actually implemented a plan that cost about $6 million to implement and achieved about 90% of the effectiveness and flexibility that the original pilot would have had it been extended. So that was probably the one that had the single biggest impact in terms of the potential. And this was an example really of cost avoidance. I'll skip to the last two and then go back if I have a minute or two. Very closely related to the time at home issue with drivers is where drivers live and where you hire drivers when they come into your network. And again, this is very closely related to the time at home issue, because if you hire drivers in areas where our freight flows are, you tend to be able to get them home and get them back out of home at a relatively low cost in empty miles. If they're hired in areas that don't fit with the network, that's not the case. Well, unfortunately, the parts of the country that provide a nice fit to the network in terms of where you'd like to hire drivers are precisely not the areas of the country where drivers are easier to hire. So we have kind of a trade-off there where in the past we have tended to hire drivers, the part of the organization that hires drivers where they're easy to hire, where they can hire them at a lower cost, and the subsequent impact on the network is never really understood and fit back against that. So using the simulator, and this was one of the nice things where actually the results that we used drop right out of the simulator. As Hugo mentioned with the value functions, these value functions actually tell us the marginal value of hiring additional drivers in one region versus another. And it turns out that in the model we were able to establish that there can be as much as $1,000 a month per driver difference in the value of a driver being hired, for instance, in the Chicago area versus in rural Alabama. And so we've used that information to balance our network efficiency with our strategies in terms of hiring policies and pay packages and advertising for drivers in the whole spectrum there. So this has turned out to be a nice fit, and we've estimated that this has been worth about $5 million a year. The last one that I'll just briefly mention, and this is related to one of the slides that I skipped over on appointment setting. We had, this was just in the last 7 or 8 months, we had one of our largest customers come to us and say that they wanted us to tighten the time windows that we would commit to on picking up and delivering their freight. I think it was from an 8-hour time window down to a 4-hour time window. And in the past, we would have argued with the customer a little bit and then probably capitulated eventually because we wouldn't have had any data to go back to the customer and indicate the impact. Well, this is a case where without any additional tuning of the model or even any conversation with the group at Princeton, we were able to simulate for a subset of the freight what would be the impact of closing these time windows down. And we found that it was close to $2 million a year. And we went back to the customer and explained that the impact of this kind of constraint on the network would incur this much additional cost mainly in terms of additional empty miles to meet these constraints because of you induce some more mismatches between drivers and loads. And so we went back to the customer and said, this is what it's going to cost to do this. How much of this are you willing to share? And the response from the customer was, well, maybe we really don't need those tighter time windows. And kind of to generalize this same one, we've taken this to a broader audience of customers to discuss different kinds of appointments in terms of how tight the time windows are, or whether it's an at appointment or a by appointment, and have been able to make very compelling arguments for our customers that there are cases when they may be giving us constraints that are entirely arbitrary on their part because they think it's a good idea or they feel it's their job to lean on us. And we've been able to go back and say, if we can do it this way, this is the cost benefit and we'd be willing to share that with you. So these are just a couple specific examples, and I think I'm just about out of time, so I'll stop here, and certainly Hugo and Warren and I can answer questions depending on what dimension of the project they concern. Thank you very much. So the question is, how can we, in light of the validation techniques, sort of establish and maintain confidence in the simulation results for a variety of different problems? And I think the answer is, I think there's a little bit of faith in there, but what we tried to do in calibration, and Hugo gave just a couple of examples, we sat down with the business and went through a number of different metrics that we could use as a benchmark that they would then feel confident that the model was behaving the way the real world worked. So we spent an awful lot of time sitting down with them and saying, okay, is this important? Is this important? And so we had, I don't remember, there were probably as many as 50 different specific characteristics of our operations that we then brought into the calibration. And through the development process, we found that there were correlations between some of them, so we could actually eliminate some of them from the calibration process. But that is certainly an issue. There is somewhat of a leap of faith there to go to a different problem. But we normally we tried very carefully to keep the calibration neutral and unbiased relative to the particular policy study we might be pursuing.
If I can just add a little bit to the answer. On the part of Schneider, so Ted is referring to a bit of a leap of faith. On our part, given the kind of engineering that Ted was mentioning that we made, it was more than just faith. It was a certain level of confidence that the kinds of rules that we had in there were robust enough that even with change in certain parameters of the operation, that still the results would hold. And one thing that I did not mention but I want to highlight is besides the engineering also, if the conditions of the network would change significantly, so for instance, at a different period of the year with different data, so a new calibration would be done with that data, and then the studies would be done with the new calibration for the new data. So tuning some of our knobs, costs, penalties, and etc. So not only we had heavy engineering, but also we always had the ability to redo the calibration if the circumstances of seasonality or the country changed a lot.
All of these are... The question was the benefits that I described, are they actual or projected into the future? All of the projects that I've talked about have been done and been completed. So in some cases, obviously, it's difficult to quantify when there are some factors of other kinds involved. But these estimates are based on work we have already done and benefits that we have achieved, and that the business leaders in the appropriate areas have come back and agreed that yes, this is an accurate reflection of their understanding of what occurred. We have a number of studies that are either underway now or contemplated that I haven't talked about at all, revolving a lot around some significant changes in how we're going to organize our capacity networks, but those are future things.
If I could just add, because I've done this with other transportation companies, without a model like this, there is absolutely no way to actually estimate the impact of a policy change. If you take an operation, run it over 6 months, measure something, change a policy, run it over the next 6 months are different than the previous 6 months. The only way to get any kind of an estimate is off of a model. And so all of these numbers end up having to be model estimates.
Yeah. So the question is, how did we simulate self-scheduling without sort of having self-schedulers in there? And we certainly didn't do anything real sophisticated with random agents or anything. But what we did do was based on the pilot that was done, we generated groups of drivers we generated requests for a time at home that we tried to calibrate against the activity that took place in the pilot. So we actually did use operationally from the pilot sort of the characteristics of what self-scheduling would mean to generate time at home requests inside the model.